Now that we understand the basic core concepts of current, we can now finally talk about the math behind current. But again, before we talk about the actual math, or actually we will do in that in a bit, I want us to also understand how to visualize this. So let's start. So current is the flow of charges, right? And mathematically, current is described as current is equivalent to the change in charge over the change in time. Or to simplify that, how many charges pass through in this amount of time? Charge over time. How many charges pass through over this amount of time? So to visualize that, let's take a look at this example. So this cylinder here, this is a wire. And look, pay attention to this weird cross-sectional part or this imaginary space that I drew. So if we were to understand this or what's going on in current, this is basically saying that these 6 electrons managed to pass through this amount of space, this imaginary space, in 5 seconds. The 6 electrons pushed through or moved through this amount of space, and that all happened in 5 seconds. So again, mathematically, 5 electrons over 5 seconds. So that's how you can see current, right? And if you notice, current is actually really similar to something else that we've already learned, which is velocity, right? I mean, look, it's just c over t, and this is d over t. And they're very similar, right? Because look, current is the flow of charges, and velocity is like the movement of something, right? Like they both kind of relate because they both sort of describe the movement of something. But for current, it's in the case of charges, but for speed or velocity, it's in the terms of, meters. And the thing about that is, if you try to notice or think about it, you can actually see some kind of problems with this kind of understanding. Because number one, where did I even get the amount of area here, right? Like I kind of just made it up. And do they also do the same things in real world problems? Well, let's talk about that here. So here we have 2 different examples. So in this case, the wire is much smaller and the space they're going through, which I drew here, is a lot shorter. Meanwhile, in this wire, the wire is bigger, and thus the amount of space they're going through is also much bigger. And notice how in both situations, 3 electrons managed to move through, right? And in both situations, this all happened in 1 second. So in the span of 1 second, 3 electrons were able to move through these amount of areas, right? These spaces. So 3 electrons pass through, 3 electrons over the span of 1 second. 3 electrons pass through this area over the span of 1 second. Okay. Remember how the definition of current is just the flow of electrons, right? The flow of charges, right? And if you try to understand this, then wouldn't you kind of see that like in one of the scenarios, the flow or the movement of electrons is much faster, right? And let me explain why that's so. In this scenario, the electrons are clearly moving through a way longer space, right? Like they're moving through this in 1 second, but it's such a big ass space, like that's really fast, right? But in this other scenario, the space they're moving through is pretty small, but it still took them 1 second to move through. Wouldn't you say that the current here is way faster, like the flow of electrons is way faster than the smaller wire? Because again, after all, they passed through a way bigger amount of space in the same amount of time, but this one went through a smaller amount of space but still took the same time. It's like saying, damn, it took 3 fat asses to like move this tiny amount of space in some sort of time, but it took 3 other people to walk this insane ass distance in also the same time. So clearly you can say that the other set of people were faster, right? And the problem that we have here is that both of these situations have the same current, right? 3 electrons per second. But if you think about it, shouldn't one current be way faster? So here's how we solve that problem.